All right, so um, today we're going to finish off the topic of epoxide ring opening, which we talked about part of it on Friday. And then we're going to move into chapter 10, alkenes. We've learned a little bit about alkenes starting in chapter 8 when we learned about elimination reactions as they were the products of those reactions. In this chapter, we're going to learn reactions that alkenes undergo. But before we get to that, we're going to have an introduction talking about structure and properties, and also going over our favorite subject of nomenclature. So on Friday, we talked about ring openings of epoxides using strong nucleophiles, where a strong nucleophile would attack the less substituted carbon of an epoxide in an SN2 process. And then we would end up with a negatively charged oxygen or an alkoxide that would then get protonated by water in a second step. When we react epoxides with our HX acids, this would be HCl, HBr, or HI, we can also have ring opening, but the order of the two steps in the mechanism is reversed. Our strong acid is going to protonate the oxygen first, and this should be familiar. We've seen this time and again in reactions of alcohols as well as ethers with HX. We always see the oxygen get protonated first. And then this oxonium ion species is going to be opened by our halide. Our conjugate base in this case is a strong nucleophile, halide, chloride, bromide, or iodide. That's going to open the epoxide and give us the product. Okay, so it's just the inverse of the order of the two steps: protonation first, followed by ring opening second. If we use our acids where the conjugate base is not a nucleophile, and that would be sulfuric acid or toluene sulfonic acid, that allows us to use a weak nucleophile. A weak nucleophile is strong enough to open a protonated epoxide. Protonated epoxide with that positive charge on the oxygen will be much more electrophilic than a normal neutral epoxide. So if we use sulfuric acid, we protonate the oxygen, and then the conjugate base is not a nucleophile, so that's not going to do anything. But if you have water in there, in the reaction mixture, then the water can come in, and it opens the ring by inversion. So the water will approach from the bottom face of that ring, giving the oxonium ion and the OH group trans to each other. And then we're going to be using the water as either a solvent or a co-solvent, so there will be a large excess of the water present, allowing another equivalent of the water to deprotonate that oxygen and give us our product. Okay, so it's also going to be a backside attack, as this example shows us here. Is our product chiral? Is this product diol chiral? It is. Okay. Is our starting epoxide chiral? No. Does it have stereocenters? It does. So it's a meso compound. Right? This carbon and that carbon are both stereocenters, but because we have a plane of symmetry, this is a meso compound. But we learned at the end of class on Friday that when you have an achiral starting material and you make a chiral product, it's going to be racemic. So in addition to the product I drew for you, we're going to also form its enantiomer, which would look like this. And we would have a one-to-one mixture of these two. And that would derive from the fact that this water molecule can attack this carbon or that carbon with equal rates. And we'll get each enantiomer in that process. Okay? So, and I should mention that we could replace the water with an alcohol such as methanol or ethanol, and instead of forming a diol product, we would have a product that had an ether on one carbon and an OH group on another carbon. And we'll see an example of that momentarily. Okay? So, an interesting aspect of these reactions involving strong acids and epoxides in ring openings can be seen when we have an epoxide such as this, where we have a more substituted carbon and a less substituted carbon. When we use strong nucleophiles, what we talked about on Friday, to open an epoxide of this type, our strong nucleophile will attack the less substituted carbon because the ring opening is an SN2 process. However, when we use a strong acid in this reaction, we end up attacking the more substituted carbon. So our chloride is going to attack the more substituted carbon of this epoxide, okay? So that tells us that the ring opening or the substitution step is not a certain mechanism. What would it not be if we're attacking the more substituted carbon? It can't be SN2. If it were SN2, we would get the product with the chlorine on the less substituted carbon. Okay, so we get this one, so it's not SN2. So then we might think, well, maybe it's SN1. Maybe we have a carbocation intermediate. What I drew here for you on this board eliminates the possibility of a carbocation intermediate. Why? Okay. I see some people wanting to raise their hands. I hear some mumblings of answers. Anybody brave enough to stick their neck out and tell us why? Yes. Okay, a carbocation is not formed. If we formed a carbocation, what would the stereochemistry be in our products? So here we have trans, because we have inversion in the ring opening step. If we had a carbocation, you get a mixture of trans and cis, because your nucleophile could attack from either side of the carbocation. Okay? So the fact that we always get trans, we can get either enantiomer, but it's always going to be trans. That tells us it cannot be SN1. That tells us there's no carbocation formed. Okay? So we have a bit of a conundrum here. We have a substitution that is not SN2, according to the result I've drawn for you over here on this board. And it's not SN1, according to the result I've drawn for you on this board. And that may seem not a possibility, but the fact is, there's no law of nature saying that all substitutions have to be either SN1 or SN2. Those are man-made mechanisms created by scientists to explain what we see in nature. And there are substitutions that can have elements of both mechanisms, and this is one of them. I like to refer to it as SN1.5 because it's in between SN1 and SN2. And this figure here from the book does a nice job of explaining what's going on in this reaction. Okay? So what happens is by protonating this oxygen, we create a more electrophilic intermediate than we had with the unprotonated epoxide. And that allows us to not form a carbocation, but have the carbon-oxygen bond breaking be initiated prior to the carbon-chlorine bond formation. Okay? So we know that there is no carbocation intermediate because of what I showed you over here, the fact that it always goes by inversion in the ring opening. So we have no intermediate between this species and the product. We just have a transition state. And in that transition state, we're breaking the carbon-oxygen bond and we're forming the carbon-chlorine bond. But there's no law that says we have to do both of those at the same rates. We just have to start forming the carbon-chlorine bond before we have completely broken the carbon-oxygen bond. So at the transition state, carbon-oxygen bond breaking is advanced. It's more than 50% finished. So to just throw out a number, let's just assume that it's about 70% broken. That's going to give us partial positive charges on the oxygen and the carbon. And if we look at this intermediate, we have two choices of carbon-oxygen bonds to break. Which of the two carbons of this intermediate would be able to better stabilize a partial positive charge? Okay, you're pointing to the one on the left, exactly. The more substituted carbon would be more stable with a partial positive charge than would the less substituted carbon. So that means of these two possible transition states, the one here is going to be lower in energy than the one here. So the reaction will proceed through the lower energy transition state. Now they drew a curved red arrow instead of a dashed line, just as their way of distinguishing and indicating that this bond breaking is more advanced than the bond formation is at the transition state. But they really should have drawn a dashed line, because you do have a partial bond between the carbon and the chlorine at the transition state. It's just only about 20 to 30% of a partial bond. It hasn't made it all the way to 50% yet at that transition state. So what that means is we have a carbon where we've mostly broken the bond, so it's lost most of the electrons in that bond, and it's only gained a tiny fraction of the electron density it's going to get by forming the new bond. So we have a net partial charge on that carbon, and so this transition state will be lower in energy than this one. Okay? So no intermediate, no carbocation intermediate, because the carbon-chlorine bond formation gets initiated prior to the complete breakage of the carbon-oxygen bond. And we know that because it always opens the ring with inversion. The new bond is always formed on the opposite side of where the old bond was. So that tells us that that new carbon-chlorine bond has to be starting to form before we've completely broken the carbon-oxygen bond. Question?
Could you also think about this as like it doesn't break completely because so normally you wouldn't have, if you had a extra protonated oxygen, it wouldn't break off. It would need something else to kind of kick it off. And this, like, it isn't completely kicked off until the chlorine gets there, but it is partially kicked off.
You could say that. We have seen protonated oxygen, carbon-oxygen bonds break to make carbocations. We've seen that with alcohols and ethers, depending on the alkyl group, right? If it's secondary or tertiary, we saw carbocations form. If it was primary, we did not. But in the case of epoxides, the easiest, you can think about it in various ways, but the way I think about it is that this transition state must be lower in energy than the carbocation. That's why it goes this way. And the reason we know it goes this way is the data that I drew for you here on this board, that we get trans instead of a mixture of cis and trans, which is what we would see if it were a stepwise process, okay? So you can call it SN1.5. It's not SN1 because there's no carbocation, and it's not SN2 because we're attacking the more substituted carbon. So it has elements of both mechanisms. So there's a continuum. There's not just an either or when it comes to substitutions. You can have something that's purely SN1, something that's purely SN2, and something that's in between. This is not the last of these SN1.5 reactions. In fact, in chapter 10, we're going to learn another one. So this is something that does happen not infrequently in organic chemistry. Okay? Other questions about this mechanism? So it's useful. This is a useful reaction. It doesn't just exist to make life difficult for students who are trying to learn organic chemistry. It is actually useful in the lab. So let's say we have this epoxide and we want to make an ether from it. So we could react this epoxide with a strong nucleophile, sodium methoxide, and then we would add water in a second step. And because we're using a strong nucleophile, that strong nucleophile will attack the less substituted carbon of the epoxide. And so we're going to get the more substituted alcohol and the less substituted ether. But let's say we didn't want that. Let's say we wanted the ether on the more substituted carbon. All we'd have to do is use methanol instead of the methoxide and add sulfuric acid. So we'd protonate the oxygen. Our methanol would attack the more substituted carbon. And then we'd deprotonate in a third step. And we would end up with the more substituted ether and the less substituted alcohol. Okay? So having these two complementary sets of reaction conditions allows us to selectively generate either of these two constitutional isomers, depending on which one we want. Questions? Yes?
So, the difference between the first one you use a strong nucleophile.
Yep.
And then the second one you just use a strong acid that's not a strong nucleophile.
Yeah, we used a strong acid with a non-nucleophilic conjugate base, and so that allowed our weak nucleophile to open the epoxide. Okay. So it gives us the same, the nucleophile opens at the more substituted carbon, which will also happen if you use HX as the acid in the nucleophile. Question?
The first example had a pretty strong nucleophile,
This one right here or this one? The very top, okay? You protonate first, yes. So that's a good question. Anytime you protonate the oxygen first, whether it's a strong nucleophile, a halide conjugate base, or whether you're using methanol or water, it's going to open at the more substituted carbon. So anytime you're protonating the oxygen first, your nucleophile will attack the more substituted carbon of the epoxide. Okay, other questions? So epoxide ring openings are quite useful in the lab. The example the book shows you is interesting because it's related to something we taught you back in chapter 3. We taught you about these two asthma drugs back in chapter 3. The one that has the long nonpolar chain is the long-acting medication that gives you relief from chronic asthma over a long period of time. The one with the more compact side chain is the one that gives fast-acting relief if you're having an immediate asthma attack. And both of these compounds can be synthesized by epoxide ring openings. In this case, we're using amines as our nucleophiles. And we taught you back in chapter 7 that ammonia, our smallest amine, is always a strong nucleophile. And we told you that other amines, in some cases, could also function as strong nucleophiles. And here's examples of that, where each of these amines is functioning as a strong nucleophile, opening the epoxide at the less substituted carbon. Okay, so epoxide ring openings are very useful in pharmaceutical industry and other aspects of organic chemistry. Other questions? Okay, so let's close the book on chapter 9 and start talking about alkenes. And as I mentioned, we've already talked some about alkenes. So we're going to review some of the things we've learned about alkenes and learn some new things before we start exploring the reactions alkenes undergo. Those reactions are going to be addition reactions. So this is a new class of reactions we have not learned. We've been focusing on substitutions and eliminations. And so in chapter 10, we're going to add a third class of reactions, the additions. First, some vocabulary related to alkenes. So you can have an alkene at the end of a chain. We'll call that a terminal alkene. You can have an alkene embedded within a chain. We're going to call that an internal alkene. And then you can have an alkene as part of a ring, and we will call that a cycloalkene. Okay? So these are all vocabulary words. There's a table at the beginning of chapter 10 in your book that shows you summaries of things we've already learned about alkenes. In chapter 8, we learned you cannot rotate about a carbon-carbon double bond, and we explained why you couldn't do that. That creates the possibility of diastereomers with certain alkenes, cis and trans isomers. And then we learned about relative stabilities of alkenes. We learned two things. We learned that more substituted alkenes are more stable than less substituted alkenes. We learned that the alkyl groups on an alkene can donate electrons to the more electronegative sp2 carbons of a double bond and stabilize it. And then we also learned that transalkenes are generally more stable than cisalkenes. So when we use the word generally, that indicates that there are some exceptions to that, and that those exceptions come with cycloalkenes. So we talked about this a little bit in chapter 8. When you have a 7-membered ring or less, those are only going to accommodate cisalkenes. It's impossible to put a transalkene in a 7-membered ring or any ring smaller. And if you try to do it with your models, you'll see why it won't work. You just cannot put them together. You can make 8-membered rings, but an 8-membered ring with a transalkene will be highly strained, and a cisalkene will be more stable. So in the 8 to 12-membered ring range, trans is more stable than cis. Or sorry, I said that backwards. Cis is more stable than trans. So the ring strain that you would have by trying to put a trans double bond in a ring of this size would make the cis isomer more stable than the trans. But then once you get to 13, you have enough carbons in the ring that 13 and up, trans will be more stable, just as it is when you have acyclic alkenes. Okay? Any questions about relative stabilities of alkenes? Okay, yes, go ahead. Yep. Yes, yes. So having a ring, having a chain of carbons spanning opposite sides of the alkene introduces strain that you don't have if those are on the same side of the alkene. And so you have to get up to 13 before you have enough carbons connecting the opposite sides of the alkene for it to be less strained and more stable than cis. So another key feature of alkenes is something we learned back in chapter 1, where we were comparing the structure of ethylene to the structure of ethane. We can measure bond dissociation energies, the amount of energy it takes to completely break the carbon-carbon bonds in ethylene versus ethane. And of course, ethylene is a higher number. The double bond is stronger than the single bond in ethane. But when we subtract these numbers, we get an approximate value for the strength of the pi bond. It's approximate because the sigma bond in ethylene is not exactly the same strength as the sigma bond in ethane, but it's pretty close. So what we see is that the pi bond of ethylene, and in general, pi bonds are weaker than sigma bonds. So that's an important thing to remember about alkenes, because the vast majority of the reactions we're going to learn with alkenes will be addition reactions where that pi bond is being broken, and in its place we're going to form new sigma bonds. So these addition reactions are going to be exothermic. They're going to be thermodynamically favored because we're breaking a weaker pi bond and replacing it with a stronger sigma bond. Okay. So in the introductory material, the book also talks about degrees of unsaturation. We're not going to go into great depth on that topic right now. We will revisit it in chapter 13. But degrees of unsaturation comes from just comparing the general formula for alkenes to the general formula for alkanes. So alkanes, we learned in chapter 4, for every n carbons, you have 2n plus 2 hydrogens. But with an alkene, you have 2 less hydrogens for each double bond that you have. You're replacing, so the two carbons involved in the double bond each have 1 less hydrogen on them. Okay. So we say that alkenes are unsaturated because they're not saturated with hydrogen. They do not have the maximum number of hydrogens that you could have for that number of carbons. So for every double bond, you have a degree of unsaturation. Rings also add a degree of unsaturation. So rings and double bonds both add degrees of unsaturation. And that's something we'll talk about in chapter 13 when we talk about mass spectrometry, because that's where it actually gives us some information about the structures of compounds. So we'll learn the term now, but we're not going to worry about any calculations until later. Okay? But what we will talk about is nomenclature. We need to be able to name alkenes. So the nomenclature of alkenes, the first thing we have to learn is that -ene is the suffix. So we have a suffix that refers just to alkenes. Okay? And so that means that our nomenclature is going to be a little different than it was with alkanes and alkyl halides because we have this suffix. So the first thing we're going to do is we're going to find the longest chain containing both carbons of our double bond. Okay? So both carbons of our double bond have to be part of the chain that we are naming, that we're using as our parent chain for this compound. Okay? Then once we found that chain, we're going to number in the direction that gives the double bond the lowest number. Okay? Now there are 2 carbons in the double bond, but we're only going to number the first one we encounter because both of those carbons have to be in the chain. Okay, so if we encounter the first carbon of our double bond at carbon number 3, we don't have to designate carbon number 4 as being part of the double bond. We just know that it will be. Okay? But we're going to number in the direction giving the lowest number to the first carbon of the double bond that we encounter in the chain. And then our third point comes from the fact that in our last chapter, we learned that OH groups have priority over other substituents. That's due to the fact that they get a suffix, right? If you have an alcohol, you have a suffix -al, as opposed to using it as putting it in the prefix of the name. Same thing applies to alkenes. Alkenes get a suffix. They go at the end as opposed to the beginning of a name. So they're going to have a certain priority level. So what we'll say is that an OH group has priority over an alkene, but then an alkene has priority over alkyl halides. Remember, alkyl halides had no priority. They're treated as a substituent, just like an alkyl group. They don't get any special suffixes. They just are treated as a substituent, so they're named in the prefix part. Okay? So this intermediate priority between alcohols and alkyl halides can seem confusing, but it's most easily understood by looking at examples. So let's look at a couple of examples of how you would name alkenes, and then these rules should make more sense. Okay. All right. So this compound has an alkene in it. So what is the longest chain that contains both carbons of our double bond? Okay, it's 7 carbons long. So what is the parent name and the suffix going to be? Heptene. Okay, I'm going to put heptene. Now we need a number associated with our ene. And there's 2 ways to do this, much like there was with alcohols. I told you there was an old system as well as a new system for IUPAC nomenclature. The new system, which is kind of silly because it's harder to say, puts that number in between the parent part of the name and the suffix. But we're going to use the old system, just like we did with alcohols, and just put the number in front of the parent name. But if you see it in the middle, you'll know that it means the same thing. It's not a big deal. It's just easier to say the way that we're going to do it. So what number are we going to put in front of heptene in this name? We're going to put a 1 there. Yes. Okay. Now we have substituents we have to name that are going to be in the prefix part of the name. What's going to go first in our prefix? Okay, what number will go in front of our chloro? Okay, so we will call it 6-chloro. And then what goes next? 2-methyl. Very good. I didn't quite leave myself enough room. 6-chloro, 2-methyl, 1-heptene. Okay, any questions? All right, so now to see how this priority issue works, let's draw the same skeleton. So let's replace our chloro substituent with an OH. So when we have 2 suffixes, the one that has the higher priority goes last. So we're going to have -all at the end of this name. Okay, so I'll just go ahead and write that for you. Heptene-ol. Now, we have 2 numbers that have to go along with these suffixes. And so we are actually going to have to put one of the numbers before our last prefix, okay? So the number that applies to the alcohol is going to go right here. What number will that be? It's going to be a 2, because our alcohol has higher priority than our alkene. We now have to number from the right in order to give the lower number to the alcohol. And now we're going to put a second number in front of the parent part of the name to account for where the alkene is. What number is that going to be? That's going to be a 6, yes. So this will be 6-heptene-2-ol. If you use the newer system in the book, it would be hept-6-ene-2-ol, which is kind of silly, kind of a pain to say. So I'm going to stick to the one that's easier for me to say. And what goes in front of the 6? We need a 6-methyl on there. Very good. Okay. All right. So you see how we apply this issue of priority of how we name differently if we have an alcohol and an alkene in the same molecule versus just an alkene. Let's see how it works when we have a cycloalkene. Okay. So here, it's understood that carbons 1 and carbon 2 are going to be the two carbons that are part of the double bond. So what we need to do is number those in the way that gives the lowest number to our other substituent. Okay? So what's our parent name going to be? Cyclohexene. We don't need a number because we know that the double bond is going to be at carbons 1 and 2, but we have a prefix. What are we going to put in front of cyclohexene? 3-chloro, yes. Okay. We don't need any numbers here in the middle because 3-chlorocyclohexene tells us this structure and only that structure. Okay. But what if it was an alcohol instead of a chloride? Okay. So now the parent part of the name is going to be cyclohexene-ol. And now carbon 1 is the carbon bearing the OH group. And so the number we put in front of the parent name is going to refer to the carbon of the alkene. And what number would go there? It would be a 2, yes. Okay. All right, so you've got the naming of alkenes down pretty well. If we have more than one alkene, we're going to use the prefixes di and tri, or tetra, or however many alkenes we have. And then we're going to have to put more than one number. If we have a diene, we would have to use 2 numbers. If we had a triene, we would use 3 numbers. So let's do an example of that to see how we would apply this. So this is a diene, and the way we do the parent name is a little different. We leave the A, we don't drop the ane, we just drop the NE. So we, instead of calling this hexadiene, which would be harder to say, we would call it hexadiene. Okay, so anytime we have to use di, tri, tetra, and so forth, we're going to keep the A from the parent name. So we'll call this hexadiene. What numbers are going to go in front of our hexadiene? The first number of each alkene. 2, 4. Okay, good. So we're going to have a 2 and a 4 here. And then we have a substituent. What's going to go in front of the 2 and the 4? 3-ethyl, exactly. So the example I chose, you could go from either left or right and get the 2, 4 numbering. So what you're going to do is use the first point of difference with our substituent. We want to give our substituent the lower number. So we start from the right, and it's on carbon 3. However, this is an incomplete story in terms of the name of this compound, because we can have cis and trans isomers with certain types of alkenes. Okay? We learned the criteria for this in chapter 8. Whenever each of the carbons of an alkene has 2 different groups, then we can have diastereomers of that alkene. So this alkene, you could say that's trans. But this alkene, you can't say if it's cis or trans because it's a tri-substituted alkene. The method we used to determine if it's cis or trans doesn't work in this case. So because the cis and trans nomenclature only works for some but not all alkenes, our friends at IUPAC created a new nomenclature system that does allow us to name any alkene that can have diastereomers. And that nomenclature system involves E and Z. This nomenclature system was created by Germans, so E and Z refer to 2 German words, Entgegen is what the E is short for. And the Z, I'll cross my Z's because they do that in Germany. Zusammen. Okay. Are there any German speakers in the class who know what these two words mean? We didn't have any in the last hour either. No, usually there's at least one person who speaks German in most organic chemistry classes. I guess the German-speaking missions are declining in numbers these days, unfortunately. So, entgegen means opposites. I happen to know German because I lived in Germany when I was a kid, and I took German in high school. But then when I served my mission in Japan, I forgot most of the German I learned. But I remember these two words because we use them in organic chemistry. So entgegen means opposite, and zusammen means together. Okay? So if you don't know German, you do have to memorize that E refers to opposite and Z refers to together. But I guess nobody in the class has an advantage since nobody knows German. So how do we apply this E and Z? Well, there's two things we have to do. Number one, we have to assign priority. And this is priority using the R and S system. Remember when we looked at the groups on a carbon on a stereocenter and we assigned priority from 1 to 4? There was a system we used for that. So we use that same system to assign priority to both substituents on each carbon of our double bond. So each carbon of our double bond will have two substituents that are not the other carbon of the double bond. We take those two substituents and we assign a 1 to the higher priority and a 2 to the lower priority. Okay? So if both higher priority groups are opposite, then the configuration of that double bond is going to be E. In contrast, if both of our higher priority groups, the higher priority group on one carbon, the higher priority group on the other carbon, are together, then it's going to be Z. So what this tells us is that any alkene that is trans is going to be E. Any alkene that is cis is going to be Z. And if it's a tri-substituted alkene that you couldn't determine if it was cis or trans, like this alkene here that has 3 substituents, cis and trans doesn't work. Now we have a method to assign it as being E or Z. Okay? Any questions about this? Yes? Okay, so we'll go through the example. So let's look at this compound right here. We've got, let's start with the alkene that's at carbon 2 and carbon 3. Let's look at carbon 2. We have a hydrogen and a methyl group. Which is higher priority? So methyl's higher priority. Then we look over here. We have the ethyl group and we have an alkene. Which would be higher priority? The alkene is higher priority because that has 2 carbon-carbon bonds, right? So we have methyl group and alkene. Are those on opposite sides of this alkene or the same side? Those are on opposite sides, so that's going to be E. So we have another part of our prefix we have to add, 2E. And then let's look at the alkene that starts at carbon 4. Is that going to be E or Z? That's also E. The alkene is higher priority than the hydrogen, methyl higher than the hydrogen. The groups are opposite, so that's also entgegen. So 2E, 4E, 3-ethyl, 2,4-hexadiene. So prefixes such as R and S, E and Z go at the very beginning of the name. If there's only one alkene, you don't need a number because we know what the E or Z applies to. But we have 2 alkenes in this case, so we have to put numbers in front. Question? Yes. So it's not incredibly efficient, but that's the way you do it. But you don't need numbers if there's only one alkene. You only use the numbers if there's two or more alkenes. Okay? Other questions? All right, so we'll stop there with our easy nomenclature of alkenes, and we'll continue on Wednesday.